The planetary model of the atom proposed by Rutherford was soon found to contain a fatal flaw. Although it was a good start, it was not supported by the quantum theory and could not explain why atoms emitted non-continuous spectrum, but also because it could not be supported by Maxwell's equations. In 1913, Niels Bohr, a Danish scientist, proposed a modification of the planetary model that looked to incorporate the quantum theory. Bohr focused his study on the hydrogen atom. Hydrogen is the simplest type of atom in that it has only one proton surrounded by a single electron. Bohr proposed the idea that electrons can only be found in special magic orbits. By magic, what he really meant was stable, and that the angular momentum of an orbit must be equal to n times Planck's constant divided by 2 pi, where n is a whole number. The genius here was that Bohr was quantizing angular momentum. So Bohr's assumptions here are pretty big ones. He was good with the idea that electrons are in orbit around the nucleus, but only specific orbits. The electrons can't just be anywhere around the nucleus. The angular momentum of the orbit must be equal to nh divided by 2 pi. The electrons contained in these orbits would not decay in a flash of light. But wait, why can we see lines in a spectra? Bohr explained this by proposing that light is only given off when the electron changes from one orbit to another. So when an electron goes from n equals 2 to n equals 4, for example, light is given off. Bohr's model is composed of two statements about the atom. The first one is that electrons move around the nucleus in a specific circular orbit. Each orbit corresponds to a certain discrete quantity of energy. This idea incorporates the quantum theory of energy by stating that the electrons can only have specific amounts of energies associated with them. Again, just like the rungs on a ladder, that electron cannot exist in between any two orbits. In order for an electron to move up in an orbit, it must gain a certain quantity of energy. If it moves down in an orbit, it gives off a certain quantity of energy. So electrons can exist in any of the orbits, but cannot exist in between. The second part of the statement says that electrons do not radiate energy as they move through these orbits. This is, of course, in violation of Maxwell's theory of electromagnetism. But as we will see in a bit, if we say that the electrons can only have specific allowed energies, then this allows us to quantify angular momentum as well. So we have our hydrogen atom. In the center is one positively charged proton, and in some orbit around it is a negatively charged electron, moving at some velocity tangent to its orbit. As with any circular motion, there is some centripetal force holding the electron in that orbit. Since this force involves two opposite charges, the centripetal force is actually an electric force. We can find the centripetal force of the electron in orbit by taking the mass of the electron times the tangential speed squared divided by the orbital radius of the electron. We can find the electric force of the proton acting on the electron by taking Coulomb's constant times the charge of the electron times the charge of the proton divided by the radius squared. Now we wrote Q squared in our equation because the charge on an electron and the charge on a proton are the fundamental charges and have the same value. Since the centripetal force is equal to the electric force, we can set those two expressions equal to each other. Really, at this point, we're interested in angular momentum, so let's solve for mv squared. We have some r's that can cancel out, and we find that the angular momentum of an electron in orbit around a nucleus is equal to Coulomb's constant times the charge squared divided by the radius. Remember that Bohr is looking at the angular momentum of the nth orbit. Now the definition of angular momentum is the radius times the mass times the velocity. We're talking about the angular momentum of the nth orbit of an electron, so we would take the radius of the nth orbit times the mass of the electron times the velocity within that orbit. Now we can take this statement for angular momentum and set that equal to Bohr's prediction for an orbit's angular momentum. We are going to be interested in this velocity in a moment, so let's solve for that. We've got a couple equations now that describe the electron moving in a certain orbit. The first one relates the centripetal force to the electric force, while the second describes the velocity of the electron within the orbit. So let's combine them because, well, math. We're going to substitute our expression for velocity into our centripetal force expression. Square everything inside there, and we end up with this beautiful mess of an equation. Now we do have a purpose here. We are interested in finding where exactly around the nucleus these electrons are orbiting. So let's solve for the radius of the nth orbit. Move the Rn squared over to the left since there are fewer obstacles over there. And one of them cancels out. We have two expressions for mass of an electron over there on the left, so let's combine those terms. Then we can divide by Kc and Q squared to get Rn by itself. What we have here is the radius of Bohr's stable orbits. And if we plug in our numbers for hydrogen, we get a radius of an orbit for its electron is about 5.3 times 10 to the negative 11th meters, which is the actual measured size of hydrogen. It actually gives us a perfect equation for the size of the hydrogen atom. Now this equation works for any hydrogen-like atom. What this means is that an atom that has any number of protons and neutrons, but only one electron, this will hold true. Granted, this doesn't happen very often. So what if we have more than one proton? The number of protons contained in an atom is known as the atomic number, and it is represented by capital Z. Say we have carbon. Carbon's atomic number is 6, so this would mean that carbon has 6 protons in its nucleus. Each of those protons has a fundamental charge, and since there are 6 of them, our total fundamental charge inside the nucleus would be 6Q. This is definitely going to impact a lot of things, and we have to account for those changes in our calculations. This is done simply by multiplying Q squared by Z. So what would happen to our radius as we increase the number of protons in our nucleus? Our denominator would get bigger, so the radius of our atom decreases as we increase the number of protons in the nucleus. Now I also want you to notice something here. Except for N and Z, everything in this equation is a constant. So if we really wanted to, we could pull all of those out and combine them into one new constant. This new constant has a value of 0.529 times 10 to the negative 10th meters, and we call this the Bohr radius. So instead of having all of those different terms in our equation, we can simply say that the Bohr radius times n squared divided by z gives us the radius of our orbit. Let's go back to our equation for the speed of an electron in orbit. The thing is, it depends on the radius of the orbit, and that can be kind of problematic. So we're going to take this whole expression for the radius of our orbit and plug it into our velocity equation. Take a moment to quietly freak out, and then start combining some terms. We have an n that can be canceled, as well as a pi and a 2, and the mass of an electron. Oh, and an h. That leaves us with a velocity equal to 2 pi times Coulomb's constant times the atomic number and the fundamental charge squared, all divided by n and Planck's constant. So this equation gives us the speed for an electron in a hydrogen-like atom. Now look how z affects this equation. Since it is in the numerator, increasing the atomic number will increase the orbital velocity. So more positive charges in the center of the atom will cause the speed of an electron to increase. So this is a basic representation of the Bohr model of the atom. The first possible orbit for an electron in this atom is a circle labeled n equals 1. N is known as the principal quantum number and is simply a way to designate which orbit is being referred to. The possible orbits in which an electron can be found is called a stationary state. These stationary states are determined by our equation for the radius of an orbit and is dependent on n equaling some whole number. To give a visual here, let's just say that when n equals 1, the orbit is found to be 2 centimeters. Note that this is a totally made-up number. It doesn't mean anything. It's just simply a way to give you an idea of how these orbits are arranged around the atom. So the first orbit, where n equals 1, gives us a radius of 2 centimeters. So the area that is 2 centimeters away from the nucleus of the atom could possibly be holding an electron. This is the first stationary state. Well then, where would we find the second stationary state? If n equals 2, then the 2 will be squared, and the orbit will end up being 4 times bigger than the first orbit. So the second orbit radius would be found 8 centimeters away from the nucleus. The same thing happens if we have n equals 3. 3 squared is 9, so the third orbit is 9 times bigger than the first, or 18 centimeters. So since the orbits are based on the square of n, the orbits are going to be more and more spaced out as n increases.